Have you ever looked at a giant bridge, a tall tower, or even the roof of a stadium and wondered, how on earth does this structure stand so strong without collapsing? The secret lies in something both simple and brilliant: the truss. A truss looks like just a collection of bars joined together in triangles, but behind the simple geometry hides a world of fascinating physics. Engineers rely on trusses because they distribute loads in such a smart way that every single member has a role to play. Some members pull, some members push, and together they create a balance strong enough to carry enormous weights. And the best part, with the method of joints, we can peek inside this hidden world. Step by step, we can calculate exactly how much force flows through each member of the truss, almost like tracing the veins of strength inside the structure. So, in this session, we'll dive into 3 powerful examples. Starting simple and moving forward, you'll see how trusses really work. And by the end, you'll look at every bridge, crane, and rooftop with new eyes, knowing the invisible forces that hold them together.
All right, let's move on to question number 1. We are asked to determine the force in each member of the truss shown in the figure. First, let's carefully read the problem and look at the diagram. We have a triangular truss with a horizontal base of 4 meters, a height of 1.5 meters, and a vertical member at the center. At the top joint, there is a downward load of 2.5 kilonewtons. At the center bottom joint, there is another downward load of 0.5 kilonewtons. At the 2 supports, on the left and right, we already see the vertical reactions, each equal to 1.5 kilonewtons upward. So, our first job is to calculate the internal forces in the members: the slanted sides, the base members, and the vertical member. Before starting calculations, let's understand the geometry. The base is 4 meters wide, so each half is 2 meters. The height of the truss is 1.5 meters. If we apply Pythagoras to the slanted member, the length becomes 2.5 meters. So the cosine of the slope angle is 2 divided by 2.5, which is 0.8. And the sine of the angle is 1.5 divided by 2.5, which is 0.6. We will need these values to resolve the forces. Now, let's start with the left support joint. Here, 3 forces act: the upward reaction of 1.5 kilonewtons, the slanted member A going up to the top, and the horizontal member D going to the center. For vertical equilibrium at this joint, reaction plus the vertical component of A must equal 0. So we write 1.5 plus Fa times 0.6 equals 0. From this, Fa equals negative 2.5 kilonewtons. The negative sign tells us that member A is in compression with a magnitude of 2.5 kilonewtons. Next, horizontal equilibrium. Fd plus Fa times 0.8 equals 0. Substitute the value of Fa. Fd equals negative 2.5 times 0.8, which is 2.0 kilonewtons. So member D is in tension, 2 kilonewtons. At the center bottom joint, we have 3 members: the left base member D, the right base member C, and the vertical member. There is also an external load of 0.5 kilonewtons downward. By symmetry of the truss, the horizontal forces from left and right cancel each other out, so we only check vertical equilibrium. That gives Fv minus 0.5 equals 0. Therefore, the vertical member carries a tensile force of 0.5 kilonewtons. Now, by symmetry of the truss, the forces on the right side will be exactly the same as on the left. So member B, the right slanted, also has 2.5 kilonewtons in compression, and member C, the right horizontal, has 2 kilonewtons in tension. At the apex joint, let's confirm equilibrium. The external load is 2.5 kilonewtons downward. The vertical components from members A and B together provide 1.5 plus 1.5 upward, and the vertical member pulls downward on the apex with 0.5. So total upward is 3, total downward is 3, and the joint is in equilibrium. This check confirms our calculations are correct. Now, let's summarize all the member forces. Member A is 2.5 kilonewtons compression. Member B is 2.5 kilonewtons compression. Member D is 2.0 kilonewtons tension. Member C is 2.0 kilonewtons tension. Vertical member is 0.5 kilonewtons tension. And that completes the solution for question 2. So, step by step, we used the method of joints to find the internal forces, and we also checked equilibrium. This is a neat example of how systematic calculations and symmetry can make truss problems very simple.
Now let's move to question number 2. This one is a bit more interesting. Will the geometry and loading make it slightly more challenging? Watch carefully how each step builds on what we learned in question 1.
Here's our truss. It has supports at points A and D and external loads acting at points C and F. At C, we have a horizontal load of 80 kilonewtons to the right, and at F, a vertical load of 50 kilonewtons downward. Our goal is to determine the force in every member of the truss and also identify whether each member is in tension or compression. Step 1 is to calculate the support reactions at A and D. From horizontal equilibrium, sum of Fx equals 0, Ax plus 80 equals 0, so Ax minus 80 kilonewtons, meaning 80 kilonewtons to the left at A. Next, let's take moments about point A. The 50 kilonewton load at F produces a clockwise moment of 100 kilonewton meters. The 80 kilonewton load at C produces another clockwise moment of 60 kilonewton meters. To balance, the upward reaction at D must produce an anti-clockwise moment. So 3 dy equals 160, so dy equals 53.33 kilonewtons upward. Finally, from vertical equilibrium, Ay plus dy minus 50 equals 0. So Ay equals minus 3.33 kilonewtons, which means a downward reaction at A. So our support reactions are Ax equals 80 left, Ay equals 3.33 down, and dy equals 53.33 up. Now let's move to joint A. At this joint, we have two members, AB and AE. Using the vertical equilibrium first, AY plus FAB sine theta equals 0. Substituting values, FAB equals 5.56 kilonewtons in tension. Next, using horizontal equilibrium, AX plus FAE plus FAB cosine theta equals 0. This gives FAE equals 75.56 kilonewtons in tension. So, at joint A, AB is a small tension member and AE is a large tension member. Now let's analyze joint B. We already know AB is pulling left with 4.44 kilonewtons. From equilibrium, BC equals 4.44 kilonewtons in tension. Vertically, we find FBE equals minus 3.33 kilonewtons, so member BE is in compression. This shows how vertical links like BE usually act in compression to balance force. At joint E, we have members BE, EC, and EF. From vertical equilibrium, BE plus EC sine theta equals 0, so EC equals 5.56 kilonewtons in tension. From horizontal equilibrium, minus AE plus EF plus EC cosine theta equals 0. This gives EF equals 71.11 kilonewtons in tension. So, at joint E, both EC and EF are tension members. Now at joint F, we have EF, FD, and CF plus the external 50 kilonewton downward load. Horizontally, EF and FD must balance, so FD equals EF equals 71.11 kilonewtons in tension. Vertically, CF must balance the 50 kilonewton downward load, so CF equals 50 kilonewtons in tension. Finally, let's solve joint C. We already know BC, EC, and CF. From horizontal and vertical equations, we find that CD equals minus 88.89 kilonewtons, so CD is in compression. This makes sense. CD is the big diagonal that resists most of the horizontal load at C. To summarize, here are the final forces. AB equals 5.56 tension, AE equals 75.56 tension, BE equals 3.33 compression, BC equals 4.44 tension, EC equals 5.56 tension, EF equals 71.11 tension. Notice that almost all bottom and diagonal members are in tension, while some verticals and the big diagonal CD are in compression. And that completes the truss analysis using the method of joints.
Finally, let's take on question number 3. This question will test everything we've practiced so far, from joint analysis to understanding compression and tension in truss members. So get ready to solve it like a pro. So here's our problem. Determine the force in each member of the truss using the method of joints. Take a look at this truss. It's a simple but elegant structure with a span of 15 meters divided into 3 equal panels of 5 meters each. The height is also 5 meters. We have two 10 kilonewton loads applied downward at joints B and C, and the truss is supported at points A and D. Let me label everything clearly so we're all on the same page. At the top, we have joints A, B, C, and D from left to right. At the bottom, we have joints E and F. Beautiful. All right, before we jump into analyzing individual joints, we need to find our support reactions. This is step 1 in any truss analysis. Let's apply vertical equilibrium for the entire structure. The sum of vertical forces equals 0. So, RA plus RD must equal the total downward load of 20 kilonewtons. Now, here's a helpful observation. This truss is perfectly symmetric. The loads at B and C are identical, and they're placed symmetrically. The supports at A and D are also symmetric. This means our reactions must be equal. Therefore, RA equals RD equals 10 kilonewtons. Each support carries half the total load. Easy, right? There we go. We now have 10 kilonewton upward reactions at both A and D. These green arrows represent the support forces pushing up on our truss. Now comes the fun part, the method of joints. We're going to analyze each joint one by one, starting where we know forces. Joint A is perfect because we know the reaction there. Let's focus on joint A. At this joint, we have 3 things. The upward reaction of 10 kilonewtons, member AB going horizontally to the right, and member AE going diagonally down at 45 degrees. First, let's apply vertical equilibrium. The sum of vertical forces equals 0. We have RA, which is positive 10 kilonewtons upward, minus the vertical component of FAE. Remember, member AE is at 45 degrees, so its vertical component is FAE times sine of 45, which is FAE divided by root 2. Setting this equal to 0 and solving, FAE equals 10 root 2, which is approximately 14.14 kilonewtons. Since this value is positive, member AE is in tension. It's being pulled. Now for horizontal equilibrium. The horizontal component of AE, which is FAE times cosine 45, must be balanced by member AB. This gives us FAB equals 10 kilonewtons. However, our equilibrium equation tells us this member is pushing on the joint, which means AB is in compression. Perfect, we've solved our first joint. Member AE, 14.14 kilonewtons tension. Member AB, 10 kilonewtons compression. Let's move to joint E. This is the bottom left joint, and we already know the force in member AE from our previous analysis. At joint E, we have 3 members. AE coming in from the upper left, BE going vertically upward, and FE going horizontally to the right. There are no external loads at this joint. Starting with horizontal equilibrium, the horizontal component of member AE must be balanced by member FE. FAE times cosine 45 equals FFE. Plugging in our value, FFE equals 10 kilonewtons in tension. Now vertical equilibrium.
The upward pointing member BE must balance the downward vertical component of AE. This gives us FBE equals negative 10 kilonewtons. The negative sign tells us this member is in compression with a magnitude of 10 kilonewtons. Great! The bottom chord member FE is pulling with 10 kilonewtons, and the vertical member BE is pushing with 10 kilonewtons. Now we're at joint B, and this is where something interesting happens. Joint B has 4 members meeting, AB from the left, BC to the right, BE going down, and BF going diagonally down to the right. Plus, we have that 10 kilonewton external load pushing down. Let's tackle vertical equilibrium first. We have the external load of negative 10 kilonewtons, the force from member BE, and the vertical component of the diagonal member BF. We already know that BE is 10 kilonewtons in compression, which means it's pushing down on joint B with 10 kilonewtons. Now solving for FBF, and what do we get? 0. Member BF carries absolutely no force. This is called a zero-force member. It's part of the structure but carries no load under this particular loading condition. This often happens in symmetric trusses due to the way forces balance out. For horizontal equilibrium, since BF is 0, members AB and BC must balance each other. This means FBC equals 10 kilonewtons in compression. Excellent. The top chord continues in compression, and we've discovered a zero-force member. Now, here's where our earlier observation about symmetry really pays off. Since this truss is perfectly symmetric about the center line, and our loading is also symmetric, the right side must mirror the left side exactly. This means member DF equals member AE, so 14.14 kilonewtons in tension. Member CF equals member BE, so 10 kilonewtons in compression. And member CD equals member AB, so 10 kilonewtons in compression. Look at that. We just solved half the truss without doing any calculations. Symmetry is a powerful tool in structural analysis. Always look for it because it can save you a lot of time. All right, let's bring it all together. Here's a complete summary of every member force in our truss. The diagonal members AE and DF are both carrying 14.14 kilonewtons in tension, shown in blue. The bottom chord member FE is carrying 10 kilonewtons in tension, also in blue. The entire top chord, members AB, BC, and CD, are all in compression at 10 kilonewtons each, shown in red. And the vertical members BE and CF are both in compression at 10 kilonewtons, also in red. And finally, the center diagonal BF is a zero-force member, shown in gray. Remember, blue means tension, the member is being stretched. Red means compression, the member is being squeezed. And gray means zero force, the member carries no load. And there you have it. We've successfully analyzed the entire truss using the method of joints. Every single member force has been determined, and all our equilibrium conditions are satisfied.
Great job following along. We've solved 3 truss problems and learned powerful engineering concepts. If you found this helpful, don't forget to like, share, and subscribe to Academic Engineering, where learning engineering becomes visual and easy to understand. See you in the next one.